Okay, well, I think we can get started now. We know that people are still arriving, and yet this is such an exciting and information-packed webinar. We want to make sure we don't wait too long before we get it started because we want to maximize the time. I am particularly excited about this webinar personally because it is an opportunity to have our eyes and minds opened to brand new possibilities using open data and open information structures to manage our facilities, every kind of built facility, be it vertical or horizontal, using information to increase our effectiveness of management and to understand what to ask for. The speakers are amazing. Stephen is an engineer and inventor. Parastoo works for the National Institute of Science and Technology, Standards and Technology. Sorry, I always get that wrong. And Kimon has been a thought leader in empowering people with open information uh, for decades. You're probably all familiar with BIM Storm. So, with that level of excitement, Kimon, you've assembled an amazing team. Can you introduce us and take us on the journey? We need to have you unmute the microphone, though.
That will help
There you
momentarily, the
go. Yeah,
technology.
thanks.
Yeah, thanks, Tony. Really excited to be here. The word for today is open, and we're talking about don't let openBIM become orphaned at handover. And it's really about how owners can extend it into operational intelligence. That's kind of the theme, but the bigger theme is just open in general. Um, as Tony described the speakers here, we have a really amazing group, and we've presented together before in different formats, but for the first time with buildingSMART. So this is exciting. If you can go to the next slide. Um, One thing, we have a lot of icons here on the screen because we kind of cross over into we wear many different hats. openBIM is part of it. I'm part of buildingSMART USA, the co-chair of the Buildings Committee. And all three of us are involved with a coalition for smarter buildings. We got a lot of words here that is part of the Linux Foundation, all about open source. And Parastoo is leading the semantic buildings group within the C4SB. I'm leading the cloud BIM group within C4SB. And PAE's Living Building is a big part of what C4SB is doing and sharing out in the open. So let's go to the next slide. So openBIM, from our point of view, openBIM is the foundation. It creates a shared context and ability to connect different domains such as electrical, networking, lifecycle, and owners need to use this information to remain usable after handover. If you click once more, Stephen, there's another icon pops up. So we see it really as today's presentation, a lot of it is about operations, but it really is about the end to end. How do you set up the requirements, go through design and construction, use openBIM, and end up in operations? But we're extending it into what are called knowledge graphs that help connect the dots between relationships and context. And the next question is, can openBIM become the trusted context layer for operations and AI, for humans and AI? So Stephen's story is an important one for openBIM. The PAE Living Building is not a typical case study where a consultant shows a successful project after the fact. PAE engineered the building, they used BIM, they moved into the building, they operate it, own it, and then experienced firsthand where BIM to operations promise sometimes breaks down. They already had one of the most advanced smart buildings, but with a problem. Instead of hiding it, they chose to open it up, and the PAE Living Building is becoming a shared laboratory where the industry can test and develop live operational data. That is what makes this unique owner, engineer, operator story and an open BIM invitation to learn together and contribute back. So thanks, Stephen and PAE, for sharing the story.
Yeah, thanks, Kimon. Great introduction. As Kimon said, my name is Stephen Lothrop, an electrical engineer at PAE Consulting Engineers. And I'll give you guys a little bit of a whirlwind tour of the building, kind of what's inside, what we're trying to connect to, and what the problems were. So a little bit of the backstory, the PAE Living Building is a developer-led living building trying to meet one of the most stringent sustainability initiatives that a building can. We're net zero energy with PV on the roof. We're net zero water, collecting all the rainwater off the roof, storing it in a cistern underneath the first floor. We also have composting toilets, so we're connected to the city sewer and water, but we don't use them. We also have a microgrid. So a lot of components into this building. And to add to that challenge, it's CLT construction, meaning there's not many places to hide those utilities. We had to be very thoughtful with our Revit model and where we're placing everything. The clash and coordination was really important in the design of this building. Taking a look at the interior, we've got radiant slabs. We've got lots of different systems, automatic fans, automatic windows to passively heat and cool the space. Here's a picture of our mechanical room, which is pretty small for a 58,000 square foot commercial building, but that's all we really need because it's designed to be a passive building. And then here's a picture of our water system. Underneath that hatch on the floor there is the 71,000 gallon cistern, and this is the clean side of the water processing. So we're processing the water into drinking water from that cistern. And another picture of our sort of water sewer system. From left to right, we have our water heaters, which when we were going through this process, originally we thought we'd use the solar to charge those water heaters, but we discovered that there's no way to communicate with them. They don't have any communication module built in. And we're still trying to work through that and figure out how could we communicate with them if you replace the board, but something we discovered along the way. Okay, moving to the right, we have in the green tank our gray water system. Behind that, in that silver column, that is our nutrient distillation column, which processes urine into fertilizer that we then sell. No such thing as waste at the PAE Living Building. And even further to the right, we have our blue composting bins that are for the composting toilets. So lots and lots of systems to control. And when we entered into this process with the Coalition for Smarter Buildings, we're trying to bring all this together to control it as one, to view it as one. And that hasn't even touched our microgrid. So we have batteries and PV. We're able to operate with the grid, reduce our demand charges, and also able to operate islanded should we ever have an outage. During the summer, we could possibly operate for weeks at a time without the grid depending on the sun. Okay, so that's a little whirlwind tour of the PLB. And I give that to illustrate all the different systems we were trying to connect. We modeled this building in Revit. That's where we did all the design. And then when we tried to recreate it in this digital twin, we realized that the systems that we had set up weren't really made to do that. Because we took our Revit, we took this 3D connected model, all these systems connected together, geospatial information. We sliced all of that into these 2D PDFs. We created more schedules. We handed that to the owner, to the AHJ, because that is the status quo in our industry. We lost a lot of that information on handover that we had in our Revit model. And even worse, after construction, when we were done with commissioning, we put all these documents somewhere safe, which could have been, in this case, a file room deep in the basement. In our case, it was just file folders, PDFs, etc. on our computers, but we spent months going back through all those PDFs to connect all our systems back together in this digital twin to figure out how everything was connected. Even though we had this Revit model at the start, it didn't flow through commissioning into operations. So we had an outdated Revit model that didn't help us when we're going to as-built this building. And one of the biggest problems we're seeing is that relationships are not built into our documents. We have different pieces of information scattered across our computers, scattered across file folders, and to figure out how things are connected together to rebuild that connectedness that we had in the 3D model, we have to do it ourselves. We have to infer those connections. But AI and our computers are not great at inference. They tend to hallucinate and make things up. And if we want to make our data computable, we need to have it be laid out explicitly. We need to start moving from implicit to explicit. And we can do that with a knowledge graph. We can do that with this thing called an RDF triple, which is just this sentence: subject, verb, object. That's all it is. So we're just explicitly saying a light fixture has a location, and that location is a particular room. And we define these terms, these subject, verb, object, with a standard dictionary or ontology. One of them is ASHRAE 223. It's the standard language that we can use to understand what we're all saying and build this common knowledge graph that we can all understand. And now our computers have something that they can understand explicitly. Let's take a look at one of these, what it looks like. So here we have a bathroom where we have light fixtures in the bathroom. You see that blue bathroom dot, says bathroom on it. But underneath the hood, there's an IFC GUID. There's something, a unique identifier pointing to that particular instance. And then we have to say what that instance is. It is of type bathroom. And that IFC GUID is what connects us back to the Revit model, what connects us back to the geospatial information. So looking at that type bathroom seems a little pedantic, but our computers like that. And you'll see right above bathroom, we have REC, stands for Real Estate Core. And that is a particular ontology, a particular dictionary. And we'll see down below, we have 223 Luminaire. That's another kind of ontology, ASHRAE 223. We can have multiple different dictionaries and ontologies living together in the same knowledge graph. We're not creating one standard to rule them all. We're creating this open and interoperable layer where all of our information can come together, and we can start really explicitly defining these relationships so that our computers can better understand them. So how do we do this? Well, we start with our Revit model. In this case, we're using Speckle to extract that information. We've been working with PNNL, and they developed this BIM to RDF tool that takes our Revit model and creates a knowledge graph out of it. So we're using Speckle to extract the information from Revit into JSON, which is just a standard data format that was easy to parse. And then we go through this map, translate, and validate step. We map all those specific items in Revit to this knowledge graph. We translate things as we go into a particular ontology, Real Estate Core, ASHRAE 223, or others, and we do validation along the way. There are particular rules that we could follow to know that our data should look like this or like that, to make sure that our knowledge graph is correct. And then we can eventually query that knowledge graph and pull information back out of it with a standard language, in this case, Sparkle, which is pretty similar to SQL, but designed for knowledge graphs. Take a look kind of in depth how that works. So on the left, we have our Revit interface. On the right, we have Speckle. Speckle is just an easy way to view the data. And it's just the same information in one or the other. But in Speckle, we have our ID. That's that unique identifier that I was talking about earlier. And then we have all the properties. And then we have the link between that light fixture and between the room. And so when we're going to create this knowledge graph, we're just going down the list of all the properties in that room and creating that subject, verb, object for each one of those. So room has a name. That name is open office. Room has a level. That level is not filled out in this example. And we just continue to go down the list. And then when we get to element ID and room ID, now we're seeing that connection. And we can know that those two are connected together in the physical location. And we can refer back to that physical location in the Revit model through those IFC GUIDs. Okay, so what does this all look like when it comes together? Well, we take our Revit model, we can create a semantic model with the PNNL BIM to RDF and other tools. And now we have this knowledge graph of how everything's connected, and we can start bringing in real-time operational data into that knowledge graph, knowing where that lives, and also simulated data and compare the two against each other. We can bring in information from submittals that doesn't neatly fit into Revit, but we can gather all that information in one semantic layer and know how it's all connected together. So this is real information we're getting from our building. We're able to know where that occupancy sensor is. We're able to know what those values mean and how that relates to the other systems in our building, how that relates to the mechanical systems, to temperatures and other things. So thank you very much for that. I'm going to hand it over to Parastoo to dive a little bit deeper into what these knowledge graphs are, and kind of the meaning behind them. Oh, and I should pause. Do you have any questions? I know that was a lot of information in one presentation.
Yeah, folks online, if you have questions, you can put them in the chat window or the question and answer window. We will give you the ability to unmute your microphone and ask the question directly if you'd like. For now, not seeing any questions. Stephen, maybe hand it over to Parastoo.
Sounds good.
Thank you so much. Okay, so let me first try to share my screen. Do you see my screen now?
Yeah.
We do.
Okay, perfect. Hi, everyone. Thank you for the opportunity to present today. My name is Parastoo Delgoshaei. I'm a research engineer with National Institute of Standards and Technology, also known as NIST. Thank you, Stephen, for the introduction. So before I get into more technical details portion of my presentation, C4SP was mentioned earlier, and just wanted to emphasize that their vision is to create an open, interoperable, and digitally connected systems that deliver greater operational value and sustainability and experience. As Kimon mentioned at the beginning of this sort of webinar, there are multiple working groups within C4SP. So if you're interested in any of that work, please join us. We always need more people to work on different projects that we're involved with. So I'm specifically convening the Semantic Buildings Working Group, and PAE, and another example that Kimon and I will talk about is an open example that you all can play with and test it for yourself and see how these concepts and technology that we're talking about today can actually work. The specific sort of aim that we have within the Semantic Buildings Working Group is to test how different open source semantic models that are out there, ASHRAE 223 that was mentioned earlier is one of them, Real Estate Core, Brick, other models are out there as well, can work together. And that's the key here. And we want to test things out, put things out so people can see and use it on their own projects. And we are confident that the work that we're doing within this working group is very essential to other working groups that are out there. And specifically with the advancements in the AI, we want to make sure that we're capturing the context for the data. And I will talk a little bit more about that, what we mean by that. So a good decision is based on knowledge and not the numbers. As Stephen was talking about, a lot of times, a lot of applications are just focusing on data, and that's just raw measurement. If we label that data, we're sort of creating and processing information. So for example, the raw measurement is 28. When we label that, we know that the temperature is 28 degrees Fahrenheit, or sorry, Celsius here. And as we categorize similar labels into a concept and provide the linkage between those concepts, we're creating the knowledge, right? These knowledge graphs, these ontologies. So here we're knowing that room A has a temperature of 28 degrees C, and that's very important. The step after that is when we sort of infer new information based on the existing knowledge, and we do reasoning on these knowledge graphs. So for example, filter X is clogged because of that there's a reduction in airflow rate, and because of that we cannot meet the set point in room A. So that is the wisdom that a lot of AI applications would need to have access on, and the goal here is to how can we define this knowledge in an understandable way, in a standard way for machines to understand. So the solution that we have been working on is a standard under ASHRAE, ASHRAE 223P, and the goal is to formally define knowledge concepts and the methodology to apply them into machine-readable semantic model that would represent the building system information that can be used for analytics, automation, and control. So going back to the path here, so we have a lot of AI-enabled applications on this side. And instead of them dealing with the direct data that's coming from the physical assets and systems in the building, we're providing that intermediate layer of putting the context in and having these knowledge graphs. So ASHRAE 223P is an example of that. But we can see that these knowledge graphs have the ability to link, so this graph can grow and capture different domains related to the buildings. The specific, you heard some of these terminology from Stephen. The specific languages and technologies we're using is from W3C, the World Wide Consortium, and the World Web Consortium, and we are using the base model. The base ontology of 223 is based on RDF. We're using Shackle as a way to constrain the model. An example of shaping is constraining the model is, for example, we are enforcing where to see a sensor in a model, and using this language, the applications can understand that as well. So a sensor placement can be along a connection, in a connection point, or a connectable reaches. All of these are concepts within the 223 world. So that would provide a way for these models to be validatable, as Stephen mentioned. Why are we using these technologies? Because they're powerful, they're extensible, they're queryable, they support inferencing, and they can create and link to other ontologies as well. So here's a very high-level overview of some of the modeling constructs. This model is about topology, not geometry. BIM World is doing a great job capturing that. We don't need to have that in our model. So we have a notion of equipment. So this is apologies for that. So a piece of equipment can be connected to another piece of equipment through the connection that has a media and a connection point that captures the directionality. And this is like a 223P graph of a fan being connected to a cooling coil through a series of connections and connection points. We also have a notion of property, which is an attribute or quality of characteristic. It can have an external reference. So for example, here in this VAV, we have the sort of the outdoor outlet temperature of the VAV that has a external reference to a BACnet external reference. Then that gets us to the operational data that we have. BIM knows about geometry, locations, the assets, and the equipment types, and if it's modeled correctly, would know about system architecture and connectivity. What can 223 bring to the table is the explicit knowledge from those pieces of equipment to the associated data points that could be live, simulation, or operational. Although it won't be covered in this presentation, we also have a way to map that to the actual control logic and the ability to validate. So those are the key extra features that we can bring to the table by having a 223 model as well. So here's one of the case studies that we have on semantic buildings working group. Is a RE1 example. So here's a Revit model, very small example, that using a semantic bridge, which is another way. So Stephen talked about the speckle beam to RDF path. This is another way that was developed by Onuma Inc. to create a 223 graph. It's just a small model. And over here, we can see that there's an air handling unit providing conditioned air to multiple rooms here. If we use a Sparkle query, again, as Steven said, it's like very similar to SQL. We can query this graph and specifically ask about which rooms air handling unit 1 is providing condition air to, and we can get all the 6 different room types that are getting the conditioned air from air handling unit 1. I talked about the operational data, and I think it's a very key important piece here to have the ability to access the operational data, in this case, the BACnet, through the different pieces of equipment that you have. And over here, we can query the graph for specific space and get the temperature and occupancy sensor. We're basically understanding 2 different domains. We want to know what's the temperature profile based on the occupancy profile. And we can see here that when we query the graph and finally get all the BACnet information that's encoded in the graph, then we can visualize basically, this is a winter day. We can see that when the occupancy is in the room, so value of 1, the temperature in the room has a higher temperature because it's a winter day. And when they're not there, the temperature drops lower, which seems that things are operating as expected. Now, the example that I just talked about, it was a very small example, just 1 unit within a residential building. As we talked about, PAE is an excellent example of an actual size building with real models. So Onuma Inc. has worked on this example of creating a 223 model of the PAE. We can see now the RDF triples, which is basically those axioms, the subject, verb, objects, 122,000 for a real building. But in terms of the size, if a Revit model for that building is 200 megabytes, this is only about 5 megabytes. So the size of the file is not that big, but it's a huge graph basically that you can write queries and get information you're looking for. And this is the pathway Onuma Inc. has taken to go from Cloud BIM to Turtle using the semantic bridge. We also, through the exercise that we did with the semantic buildings and other partners, someone developed a KNX model, which is similar to BACnet, that talks about the communication between the actual pieces of equipment, and created a KNX graph for the equipment that were in the BIM model. And by preserving the IFC GUID, we can see how these 2 graphs can be linked. So these graphs can grow, but they can touch other domains. If you're interested to talk about control, if you're interested to talk about the real estate aspect of things, they can sort of align with other graphs as well. So now the question is, how will these models get created? If it's a small example, someone can technically handcraft them. I have done it. But we're hoping in future, in the application of AI, we can semi-automatically generate these graphs. I mean, part of it could be coming from your BACnet and BAS systems, could be coming from BIM or other IFC models, like the one that the Speckle BIM to RDF or the semantic bridge. It could be the equipment supplier who's selling for example, an air handling unit to the owner. Their piece of equipment can come up with a, for example, 223 step, or the control vendors. But the key important thing is that what we're trying to advocate for is this is a digital asset that building owners should ask for, because down the road it can help them and benefit them in the ways that they may not even envision it to begin with. In terms of the status of 223P, we're now in the process of doing the 2nd publication and hopefully the final publication review. And when we get that result back and address the comments, hopefully if there aren't any substantive changes, we can go to the actual publication. And beyond that, if hopefully when that is published as an ANSI standard, there is a growing demand and interest from ISO TC 205, which is the Building Environment Design Committee. And they are the home for BACnet International's ISO standards. So they are interested in sort of adopting that as an ISO standard as well. And with that, I'm open to any questions. And after that, Kimon will talk more about the use cases, the case studies, and the importance of these technologies that we talked about in the AI world. And thank you for your attention.
Thanks, Parastoo. And maybe launching off of your slide about information, knowledge, and wisdom, I want to focus on the knowledge and wisdom that we're getting to, which is pretty exciting. And I've presented this before as intelligence at the Greenbuild conference as being the new sustainable resource. And the way we capture intelligence is knowing more than just the information in the building. So in BIM, a lot of times we kind of focus on the attributes about an asset. An air handling unit has A, B, C, D, and E. Very important stuff in context of knowledge graphs and everything else, because with what you described and what we're doing with the PAE building, we're capturing the wisdom and the knowledge to be able to get beyond just the raw data in the buildings. All three of us are presenting at USGBC and Greenbuild. Actually, in a few weeks, even there's an online session. But LEED version 5 is shifting from a checklist to actually validating the metrics from a building, which fits in exactly with the storyline, because you can obviously create data about a building by doing checklists or saying this is happening and getting a plaque. But if you can confirm what it's doing with metrics for a year, which is what LEED version 5 requires, it becomes real, it becomes open, it becomes accessible, it becomes valuable. We've talked about cloud BIM. It's a generic term in terms of getting data in a BIM in a cloud-based format. And at Onuma, we've been doing this for years. We feel that having accessible data in the cloud, as well as the full BIM model for design and construction, then you can get into portfolio level management like we've done with California community colleges for years. It's about making the data accessible so you can get the knowledge and wisdom out of it, and making it connectable to other systems, which is critical to all this. There's no single application that can do it all. So Parastoo mentioned the RE1 model, which is in parallel to the PAE Living Building. It's a one apartment out of an 18-story building with a lot of data. You saw that apartment unit that was shown on screen, and we've been using that for testing and development, and in fact, it's even posted on GitHub. So that's another unique piece of what we're showing. We're not only showing slides, we actually have the real data with the real buildings, with real sensor data available for those that jump in and participate. And this is kind of the process of design and construction in BIM, get it into the cloud BIM format, which is a working group within the C4SB, and then the semantic bridge of connecting the cloud BIM version to the knowledge graphs that Parastoo showed. So I'll go through that next. And the BIM that came from PAE, there are about 3,000 assets out of a very detailed model, very detailed geometrically. The problem we ran into in PAE came to us with this problem is that we have a lot of geometry, but we have very little of the data in the model, even consistency in standards. So just basic openBIM, buildingSMART related standards for BIM were not all there, but now they are. We're slowly getting into updating that and then preparing for future versions of it and learning along the way and posting it to the C4SB. So this is not, again, not just pretty pictures. We're actually capturing that information. The original Revit model was 306 megabytes for MEP, 85 for architectural. An IFC output from that could be 900 megabytes. We identified 3,000 assets. There were, as Stephen mentioned, there were Excel schedules, PDF file, wire diagrams about how things are related. All the knowledge and information that engineers and architects put into a building, if it ends up in a PDF file with single line diagrams, yeah, you could possibly use AI to extract from that. But if you want consistency and not using too much inference, you say A is connected to B, the electrical panel is connected to that, you need the RDF knowledge graphs that we worked with. We took that large BIM, we created a cloud BIM format in Onuma, which is about 18 megabytes, which has enough geometry and context to connect to other information, and it can go into portfolio level with many many buildings as well, and the load time is much faster. So you don't always need the full detailed model. In certain contexts you do. In this one, we actually stripped it down to the minimum that's needed. We talked about speckle as being one way to look at it. So there's multiple paths. There's no single application to do this with. And that's the beauty of open standards and open source, is you can use many applications to get to the same point. And then from this Cloud BIM format, we created the semantic model, which is 120, over 122,000, or 127, I think now, it's actually growing, triples. Each triple is these dots there that say it's essentially the wiring diagram in digital format that AI likes to use to query. So it doesn't have to guess where the wires are, it's all there, and it becomes real time. And the semantic bridge that was mentioned connects the context model, the BIM, to that knowledge graph. And then we used as a minimum IFC GUIDs to wrap it all together. So you don't need to take the full IFC model into a turtle file. You still have the relationship, but if you have it all together, then you have a semantic model, you have the full model, you have the cloud model, and you have it ready to go live and in the cloud. So let's show a quick video here of that process. This is the PAE building now in Portland in Cloud BIM format in Onuma. We have Skycentrics, which installed a router in the building that broke through the 8 systems that were in different proprietary dashboards. So now when we click on the building or click on an element and show us the display, it's showing live data streaming from the PAE building through the cloud, through Skycentrics, into Onuma in this case, or other applications. Here's a semantic bridge now side by side with the Cloud BIM model. So the semantic bridge allows the RDF knowledge graph to be viewed, created, and updated. So in an operational model, nothing stops. Everything starts shifting and changing. A new piece of equipment's added. One is taken out. Pieces of data were missing. A lot of data can't even be captured in BIM because there's non-geometric data, business rules, and other things like that, that need another knowledge graph. And that's the beauty of these knowledge graphs. You don't have to all agree on one format. You just have to agree on IDs that link to each other. Here's a use case for which I'll talk about later about emergency planning and response with the same building, not only measuring occupant comfort levels, but measuring if a fire breaks out, where are people sitting and where is a fire spreading, for example. That's what these color coding is about. So there are many use cases for the same data. And these use cases need to be focused on specific. I need to see a dashboard with occupancy and CO2 sensors in relation to a floor plan to make a decision for occupancy comfort or for emergency planning. And that's the most exciting thing about all this is once you think in terms of it doesn't have to be in one application, then the world opens up and AI can use this data and you can start having a conversation with this building. This is the Skycentrics interface now with somebody chatting to the building and saying, create a dashboard on the fly. What room is the battery energy storage system in? What is the total battery capacity of the building? You can go on and on just having chat-based conversations, which pulls up dashboards on the fly. Static dashboards that are built once and used in only one way are fading away, in my view, and I've heard this at other conferences too. If you have the data and it's accessible in an open format, you can build a dashboard on the fly. You can even build applications on the fly, which I'll talk about next. So this is a dashboard view, the context of the building, and this is all possible because PAE decided to take their building, share it with the industry, decide how to fix the broken connections, get to the knowledge and wisdom that Parastoo talked about, open up AI into the building, and start having many applications interacting with the same data. Okay, so let's move on. So this is one use case. We said, okay, if we see energy data coming from Skycentrics in context of the building, if you only have a dashboard and only have data, you don't know where that thing is happening in the building. Marrying the context, the BIM, the open BIM, to the data lets us see it in context and act on it. In this case, it was a low battery level warning. The low battery level warning, we put a business rule into that. It says if it gets to this point, trigger a work request that started from Skycentrics low-level battery, went into Cloud BIM, into Onuma in this case, triggered a BIM Genie work order automatically. So this is digital twin territory where you start having the conversation of the building, triggering things happening through the building. And this is just the very, very beginning of this use case and different examples. So back to what do we need in BIM? These are attributes that came from the Revit model in PAE. We identified a few key attributes that need to be added to align with ASHRAE 223P. So for example, a semantic class. This is an air diffuser. We need to have at least a common language in semantics and ontology, so we have these common connections, the minimum touch points, the connection points between systems for electrical on the left, for mechanical on the right. So we're writing this into the standards next for how do we do this next time for PAE or others, and we're posting all of this on GitHub as well. Here are the things that you need to ask as an owner. Put this into your contract, that you get this data in the model with these names, and don't overburden it with making it too complex. We already have incredible complexity in all these systems, and the RDF knowledge graphs, you don't need to have it all in one format or one protocol, one standard. You can just say BIM has this the schema here, ASHRAE 223P has this here. What are the common connections between that? And as soon as you have that, that's all you need to create that cloud. There's a lot more to it than that, but essentially it's that. If you overcomplicate it and make it very difficult to understand, then it becomes very difficult to implement. So we're looking for the minimum to get the maximum output. And that's what the semantic bridge does as well too. It takes the detailed BIM, takes it into operational cloud BIM, connects it to the semantic model RDF, and has two-way connectivity between cloud BIM and the semantic model as things change in real time. If somebody adds a piece of equipment, it gets updated. So here's the semantic, the bridge on the left, the cloud BIM simplified 3D. Intentionally, we've intentionally stripped away the details. We can always go back to the details if needed, but you can find a panel on the wall without seeing the nuts and bolts of how it's screwed to the wall, for example. I mean, I know that's extreme, but that's the case. And you can visualize the connections, because if all you have is a knowledge graph and wiring diagrams on the left, you don't know where that thing is in the model. Therefore, you can't make a decision. Imagine 127,000 pieces of data just as a knowledge graph. It looks beautiful, but it is meaningless without the context. And I think that's where the openBIM opportunity is. If we think in terms of openBIM as being the interface to the world that connects to the detailed data, and then you put AI into that and start having a conversation so you know where things are, it starts showing the decisions that can be made. Dennis Sheldon from the RPI Institute and his researchers took this on another path with IFC-LD. So we're not saying there's only one way of doing this, and they use the same RE1 model for some of their testing. And because we open sourced that model and shared it, others can start testing it, and we can start sharing the context. 2 weeks ago, we opened up a challenge with the RE1 RDF knowledge graph. We said if we hand it with a use case of emergency responders, and we had actually Fire Chief Esch and others give us input on what does a fire department need to respond to a building. Fire departments go into a building blind. They don't know what the floor plan is. They don't know what the context is. They don't know what the equipment is. They don't know what the wall material is, the floor material. Even though all these fantastic BIMs are out there, they go in and just reverse engineer the building while the fire is raging. So we said, if we share a format that says, I'm a room, I have a piece of equipment in here, I'm connected to a panel on the first floor, to the fifth floor, there's a fire panel here. So the relationships and the knowledge graphs are not even immediately in the same context. They could be actually in a utility plant down the road. There's a utility plant online, for example. That's a knowledge graph element of knowing how to react to the environment, back to the building, back to the meaning. Why is this room at this temperature? It is this temperature because it's a conference room, or it's an operating room in a hospital. Can we have the electricity go down for 5 hours? Maybe in a conference room, absolutely not in a hospital. So the exact same piece of equipment has different meaning in different context. And with this approach, you can infinitely scale it. You can have infinite number of schemas. They can be mapped to each other, and you can have a prompt window in the middle to have a conversation with a graph that is accessible, as long as it's accessible. If it's locked up in proprietary formats in places that you can't get to, then you can't have the conversation. One kind of concerning trend I'm seeing at buildingSMART for years, we've been focused on getting BIM applications to talk to each other in open standard formats, Revit and ArchiCAD and Bentley and all that, all important stuff. Now with AI and the technology, every one of us is becoming an application developer. We're seeing architects and engineers building their own applications, which is fantastic. but I'm also hearing the word, and our proprietary application does A, B, and C. In other words, we're going to have thousands of proprietary applications to deal with now rather than 5. So it's important to have that conversation in the industry as new applications get developed to think in these terms, because if you create an island, then you're really an island. You're not connected to anything else. So the turtle file RDF knowledge graph, we put it out there in 6 days. We had teams using that. We said, preserve the IFC GUIDs, add something to it, give it back to us. Duncan Green, who's online, I see his name, jumped in with KNX, and within a few days, he added KNX schema data, KNX standard data to the knowledge graph and gave it back to us with no interaction other than, here are the rules. IFC GUIDs, knowledge graph, give it back to us. We're going to check it. And within a few days, we had that, and another team was doing the same thing. So we had a lot of things happening with this fire scenario. We're looking at it from a openBIM perspective. If systems can start talking to each other and knowledge graphs are on top of it, they can say there's a fire in this floor, report it to the panel on the first floor. Here's the minimum information you need for the fire department to turn off certain things in the building, the turtle file that's giving the instructions. And it turns the complex data into queryable and instant clarity, with instant clarity, because it's explicit. A is connected to B. It's not A might be connected to B, like Stephen described. When you have an explicit line between things, AI does not have to guess, and neither do humans. So where's the failure going to happen? So this is kind of an overview of the scenarios that we've been building. You have a building with BIM. You have knowledge graph on the right. You can have a scenario of responding to a fire, responding to comfort. As long as you have access to that knowledge graph and data, it's infinitely scalable. And we're going to continue this exercise. So whoever has solutions and interest in jumping in, let us know. We're trying to keep graphics for emergency responders simple so they can get to it. And each use case has a different view of the same data from many different applications. And this can scale out to city and other types of uses as well. So I think we got through, and we actually left 10 minutes to the end. Either we can take questions directly now, or we can have a conversation between us if there are no questions. I think we've had some questions, but as we kind of finish off here, here are our contact information. We publish a lot of this PAE story on automated buildings. I think that's a typo. It's actually automatedbuildings.com. It shouldn't say AI, but you see the name there. If you go there are, I don't know, 10 to 15 articles about the PAE Living Building. Okay, so let's take questions.
That was great, Kimon. Thank you.
Thank you, Kimon.
I know Daniel left, but I think his question's still a good one that maybe we could chat about. So what validation layer is needed between the knowledge graph and the AI wisdom step? So inferred recommendations remain traceable, trusted, and operationally safe.
Parastoo, I can answer part of that, but maybe you can jump in.
Sure. Yeah, you can answer and I can share my perspective.
Yeah, so the part of it, you have to have the rules inside the knowledge graph, right? So for example, if ASHRAE 223, when ASHRAE 223P is used in the semantic model that semantic bridge that we showed, you can't physically connect two objects without using the right classification. For example, you can't connect a water line to an electrical line. It's as simple as that. You have object A and object B cannot be connected. So there's built-in kind of rules that kind of check on itself. And there are other tools that can start querying and asking those questions. So you can say, find errors. And there's many different ways of doing this. Once the data is machine readable, you have many different tools either to go through the data, and then from the context perspective in the model, you can have a conversation with the model and say, where is this thing? Or should this piece of equipment be in close to this space? You can even have rules like that relate to location and context and what that thing is doing. So that's my view of it, but I'm sure you have a lot more.
No, I was just going to say that I just want to make a clarification here. So a valid 223 model doesn't mean it's a correct model. That's first of all, right? You can define correct in terms of what it is representing for a building. I can have a valid PAE model, but that may not be what the actual ground truth is in the building. And that's something that the governors come and like through the different sources of information that you collect from the building. Could be the BIM model, combine that with what you get from the building automation system, with other artifacts that exist for that building, the drawings, everything else. You can make sure that your valid 223 model is an actual correct model of your building. So that's an important clarification I want to make here. Now, the important piece about the wisdom in inferencing. So we have validation rules in 223. We have validation rules that will tell you that, for example, the example that I talked about in terms of the actual location of the sensor, if you define a sensor in a physical room, you're going to get a validation error that this is not a valid 223 model because we expect to see sensors in a specific location. There are inference rules that, in this case, in this example, that would kind of bring wisdom. Those are more actually, I would say those are domain specific. That's the actual engineering or domain expert knowledge that you can sort of encode those into shackle rules. And then, for example, if you expect to see like that I have a pressure drop and there is this and that, then infer that the filter is clogged, right? So that is inference rule, that looking at the patterns that you see in your ontology, you can deduce new information, what we call here a wisdom. So again, there are two sets of rules. One is the validation. We want to make sure we're defining a valid model. We're not violating any constraints. But the other rules are inference rules that you can sort of draw new information based on the facts that you have at the graph. And those are two different separate things. With the validation, it's more of like your expectation of where to see things and how things should be related to each other, versus for the inference is that when you are seeing a pattern in the ontology, you want to infer a new information that doesn't explicitly exist in your ontology.
Absolutely. Maybe to add one more quick thing from an architect's and engineer's perspective, and Stephen, maybe you can jump in on this. There's also the decisions that are made at the point that you're actually engineering the system. Somebody's being explicit about saying this is connected to that. I'm designing this room of this size, or I'm putting the door here and swinging it that way. All of those decisions that end up in the model are driven from some business rule or engineering rule or architectural rule. And that's what we're also capturing. That's important, I think. And there are millions of those. If you start exploding it out, it just starts ballooning in size. And that's the part that in that cloud of decisions that are made, some of them are more critical than others, and some of them are more important in the context that we showed. So you don't need everything about the building, but you need certain things for that emergency planning scenario, for example. But those are engineering and architectural decisions that are critical and are the biggest opportunity, I think, for building smart. And this domain here is, and we've already essentially been talking about that for years, but this is why these decisions are important to be captured in an open format that can lead into these knowledge graphs that can then be used day to day.
Yeah, as an example, one of the things we noticed as we started monitoring the circuits on the building and bringing it into the Onuma platform was that some of our voltages were either too high or too low. And those are rules that we have in Revit. We define a voltage system there, electrical system, but we're not necessarily defining the tolerances within Revit, but that can be encoded in semantic model and relate back to the operational data, so we can start getting those validations in real time that this voltage is too high or too low. We might have a problem with equipment, and then the AI can infer from there. And it's not even really inferring at that point. It's just noticing that the rule is being broken and bringing it to our attention.
Yep.
I also want to say the semantic bridge, I think, was really the missing piece in all of this for a long time. When people would send me these turtle files, I would just kind of have a panic attack. They're overwhelming, to say the least. And to be able to interact with that data easily and click on something in this cloud BIM model and see what it's connected to is just the kind of magic.
It is magical. Yeah, I agree. One thing else, I wanted to mention something else about the previous discussion. So shackle, which is sort of the language that we can use to provide constraints. There was a project with some of the DOE labs that they have implemented Guideline 36, the sequence of operations, the ASHRAE guideline for optimally basically operate your building systems. They have defined shackled rules for that. Um, and that would actually implement the sequences, some of the sequences in Guideline 36. And the importance of that is if you have a sort of a 223 artifact and you can test it against sort of the shapes, the Guideline 36 shapes, then you would know as an owner if your building has all the information that guideline would need to operate, which is very valuable because sometimes as a building owner, you may want to know, do I need to pay some extra amount of money to get another point for my BAS system? But if you actually know what you have, and if you have like one more thing, there is another sequence that you can do, which at this point you're not capable of. You can formally validate that. That's the true power.
Absolutely. So we're getting close to the hour here. I
Yeah.
think this is recorded and it's going to be shared from what we understand through buildingSMART USA.
Yeah.
There's probably a lot more questions. The three of us actually have a whole series of conferences that we're hitting after this.
Yeah.
Next week at SimBuild in Minneapolis, and we're doing green build sessions, and I'm at the AIA National. The three of us are also going to be at Green Build in New York, I believe. It's being scheduled right now. So catch us there. Catch
Or
us online. Yeah.
or send us emails. I see that there's a LinkedIn request. I'm personally not very active on LinkedIn. I do see the messages, but I will try to be better with that. But yeah, send us emails, send us messages. We'll be happy to talk and answer any questions that you may have down the road.
Yes. Well, thank you, team, for an eye-opening, well-constructed, demonstrably practicable view on how we can actually use open standards information to increase the value of built environment. As you pointed out, several people will be viewing this on YouTube. In fact, we know that for buildingSMART USA webinars, two-thirds to three-quarters of the people who view this will be doing it after the fact. And so they didn't have a chance to ask questions. Kimon has contact information up on the screen right now. We will not edit this out. So be sure to get in touch with this team. There's so much that we can all do together. So with that, I think we'll close this session. Thank you again, team, for a great hour together.
Thank you for having us.
Yeah, thank you all.
Thank you all. Bye.
Bye.